Dr. Leslie Benet. He is a professor of bioengineering and therapeutic sciences at the Schools of Pharmacy and Medicine at University of California, San Francisco. So he has hundreds of publications and books and patents, really too many scientific achievements and accolades to list here. But he's truly a world-renowned expert in the areas of pharmacokinetics, pharmacodynamics, biopharmaceutics, and drug discovery, or drug delivery. Some of his recent work has addressed deficiencies in vitro, in vivo extrapolation, and as well as our understanding of clearance processes.
And the other thing I'm really pleased about is finding on the program that I'm speaking before Dr. Oprea. 15 years ago, Dr. Oprea and I discovered each other and published a lot of papers. This is the first time we've ever talked together on the same program. So I raise the problems, he solves them. Okay. So for the past 8 years, our laboratory has been concentrating on trying to understand why we do so poor in vitro-in vivo correlation predictability, both from theoretical and from experimental evaluation. So what do? We take a drug molecule, you've discovered it, it's not my problem. You've discovered the drug molecule. We put it in a beaker, and we try to figure out how it gets eliminated so that we can predict its pharmacokinetics in humans before we ever give it to animals or give it to humans. We do it in hepatocytes or microsomes. We take that data and scale it up, considering that we're looking at just a microsome or a hepatocyte, scale it up to a whole liver. Then we predict what's going to happen in the whole liver in terms of clearance intrinsic. We pick up some kind of model that says, okay, now I can take that information and put it to discover what the clearance in a human is going to be. And this model is the one that we use most of the time, which we used to call, or we still call, the well-stirred model. And then we say, okay, now I'm going to predict everything that happens in patients and be able to know what goes on. But it doesn't work. And we've been doing it for 50 years and still haven't discovered when it doesn't work. So about 7 years ago, Christine Bowman and I went back and looked at the literature and said, okay, how good are we? We're terrible. We get it right 1/3 of the time. We get it wrong 2/3 of the time. What's going on? Why can't we get it right? So we've come to believe that the failing is not experimental, but theoretical, and that it's really the problem that some of our basic science is wrong. And can I convince you? So what is the correct hepatic mechanistic model to convert this measured, scaled up in vitro intrinsic clearance value to in vivo clearance values? So on the first slide, I showed you this well-stirred model where QH is the hepatic blood flow, fraction unbound in blood, the clearance intrinsic, and in your incubation meter correct for the protein binding in the incubation. And it's universally believed that well-stirred model was completely unphysiologic. We got it from chemical engineering, and it is completely unphysiologic. And so we've spent a lot of time over the last 50 years developing other models, parallel tube, and a multitude of what are called dispersion models that are more physiologically relevant and should do better. Although most studies investigating hepatic elimination of the isolated perfused liver, the way you do this, the way you find out what the right model is, only way you can do it is take an isolated perfused rat liver and figure out what's going on, how does the data fit which model. And although the majority of what we do, today we have these very sophisticated physiologic-based pharmacokinetic models and companies that will allow us to make all kinds of predictions, we use this simple physiologic-based well-stirred model most of the time. But some people say, well, it's completely unphysiologic, so why shouldn't we use a more physiologic model like the dispersion or the parallel tube model? So as I said, the well-stirred model, completely unphysiologic. So we went back and looked at the experimental data and said, are there any experimental perfusion data that preferentially support the more physiologically relevant models, the dispersion of the parallel tube? And the answer is no. There is no data that supports these other models. Everything seems to fit this terrible unphysiologic model. So what's going on? So last year, we presented a new derivation of the equation relating organ clearance to organ blood flow, intrinsic clearance, and fraction unbound. Those are the terms in the equation, eliminated by metabolism or biliary excretion. And it appeared in Pharmacology and Therapeutics. And what we did was go back and look at something you all learned in your first physics class, and that was Kirchhoff's laws, and define it in terms of pharmacology and use it to define organ clearance. So when you took physics, you completely forgot this, but you remembered you took it when you took your first physics. Gustav Kirchhoff, back in 1857, developed laws to describe the motion of electricity in conductors in one paper and in wires in another paper. And since then, Kirchhoff's laws have been applied to heat transfer, diffusion, drag force on falling objects, but not to pharmacology prior to our paper. So the take-home relevance in our paper from Kirchhoff's laws is that when two or more rate-defining processes are in parallel, the total value of the reaction parameter is equal to the sum of those rate-defining processes. While when two rate-defining processes are in series, one following the other, the inverse of the parameter is equal to the inverse of the two rate-defining or more processes. That's Kirchhoff's laws. And basically what we've shown is that you don't need differential equations anymore. You can solve all the reactions that go on just by looking at Kirchhoff's laws. So what's a rate-defining process? A rate-defining process says at some point your clearance can be equal to that number. So for example, the upper limit of hepatic elimination should be hepatic blood flow. So a rate-defining process could be hepatic blood flow. You don't need, even though a whole bunch of other things are going on, you only need to know hepatic blood flow to predict its clearance. If we look at a series of metabolic reactions going A to B to C to D, if that first step is really slow, it's the rate-defining process. And even though you have all these other steps, everything in the process is going to be defined by that first reaction. So Kirchhoff's laws really apply to rate-defining processes. And we need to separate rate-defining from rate-limiting processes. Rate-limiting is the upper limit and the lower limit. So the upper limit in hepatic elimination is hepatic blood flow. So the rate-defining process, the rate-limiting is the same. But the lower rate-defining process for hepatic elimination is fraction unbound times intrinsic clearance. And it isn't necessarily the rate-limiting process. For example, if you had liver blood flow of 1,500 mils per minute and fraction unbound times clearance intrinsic of 750 mils per minute, actually clearance is 500, so it's lower than the rate-defining process. So let's consider some parallel processes. In the liver, parallel processes, two things going on independent of each other: clearance metabolism, clearance biliary excretion. One doesn't affect the other. Let's look in the kidney. What's going on in terms of parallel processes? Filtration, secretion, and reabsorption are the two parallel processes. And so we just add them together and we get the clearance. So neither of these equations are new. They're simply written based on Kirchhoff's laws. Parallel processes, you add them together. Now let's look at in-series processes, where it's the inverse. So you have an entering process and you have a leaving process that goes on in the liver. The entering process is blood flow. The leaving process is clearance. So I take those two, those are the two rate-defining processes. I sum up the inverse. I solve the equation. And I get this simple, very familiar equation, which we have thought for 50 years was the well-stirred model. But in fact, from Kirchhoff's laws, it said it's the only model. It's what is happening in the liver. So I derive that equation making no assumptions related to mechanistic characteristics of hepatic elimination And we now understand why all that data only fits what we thought was the well-stirred model, because it's not the well-stirred model. It just happened that we made some mistakes that gave us the right answer. I'm very happy about that because I'm the author of the first paper that did that model in terms of what was the well-stirred model. But I've now made a major discovery that says everything we've done for 50 years is wrong, but in fact, it doesn't help at all in what I'm trying to solve, IV-IVC. Because I was using the right equation all along, I just didn't know why. So what are we trying to predict? What we're trying to predict is the clearance that we know in humans is going to be the important characteristic in therapeutics. And how do we get it? Basically, first of all, we need a definition for clearance, and there really isn't one specifically that's operationally. I worked with some chemical engineers at Berkeley, and we published a paper that said, operationally, the only way you get clearance is the amount eliminated divided by the exposure driving that elimination, or at steady state, the rate of elimination by the steady state exposure. So there's only one valid definition. So what are the clearance? These are the clearance values we're trying to predict. So we're not trying to predict what happens with inside the liver. We're trying to predict amount eliminated divided by exposure. And yet we've been saying we really need to predict what's happening in the liver. No, we don't need to predict what's happening in the liver. So why do we want to know clearance? Well, as indicated, knowing clearance, we can predict exposure. And knowing how clearance changes, we can predict changes in exposure. And it's exposure that drives efficacy and toxicity. It's exposure that we use to make clinical medicine decisions in how we treat patients. So therapeutics is governed by exposure. Therefore, if we could predict clearance for a new molecular entity independent of experimental measures, this would be a tremendous boon. And there's lots of data out there. All you AI guys are going to solve this for us, so I can do this. I don't have to run any more experiments. But next best would be if I can do some in vitro measure and predict clearance. And that's what I'm addressing, because that's what we've been trying to do for the last 50 years. The trouble, I believe, is that we have faulty theoretical concepts. And I've presented one of them in terms of the model. Let's look at another. Let's consider a physiologic-based model for a study where venous concentrations are measured over time to determine clearance. So this is what we're doing all the time. We're taking this measurements and we're putting in this model, and we're going to say we're going to predict the drug interactions, we're going to predict pharmacogenomic changes, we're going to predict physiologic changes, and we actually do a pretty good job if we know the clearance beforehand. If we're bottom up and we don't know the clearance, we actually don't do a very good job, but that's what we need to be able to do. But let's look at this carefully. Let's take a drug that is only eliminated in the liver. And so what's going to happen, concentration of drugs is going to come into the liver and it's going to come out. That's where the clearance that's important is what we're trying to predict. But we don't measure that concentration coming out of the liver. That isn't the clearance we're trying to predict. What we measure is the blood concentrations from all the organs coming together with this fast cardiac output. So it comes into the heart, goes up to the lung, to the heart, and then comes out on the other side. So in fact, what we've been measuring all the time, as long as there's no elimination in the heart and the lung, those venous concentrations are in fact the arterial concentrations on the other side. So we're not measuring what comes out in terms of what's lost in any of the organ that eliminates drug. We're measuring everything together. So in fact, what's in the literature that we're trying to predict is an arterial clearance, even though we're measuring venous concentrations. And all published clearance values are arterial clearances. And arterial clearance values are not the same as the clearance that happens in these organs. We don't really care, because that's not what we're trying to predict. We're not trying to predict what happens in the organ. We're trying to predict what happens in the whole body. So there's no value in considering mechanistic models of hepatic elimination in IV-IVC predictions. So why are we not getting it right? Do the poor IV-IVC predictions result from theoretical errors related to the individual parameters? So let's look at the individual parameters. What we're seeing, if we take high clearance drugs, if you look at the data in the literature, and there's hundreds of data in the literature like this, what we see is that as we get bigger and bigger clearance, higher and higher extraction ratio, we do a poorer and poorer job of predicting. So on the right-hand side is the predicted, on the x-axis is the observed. You can see as we get higher and higher, we do a poorer and poorer job. When we looked at that, we said, there's something really obvious here. These high clearance drugs are blood flow. And what blood flow are we using? We're using hepatic blood flow. But I just showed you that actually we're trying to predict arterial clearance. So maybe we should be using cardiac output. And so what we did was took all the data in the literature and just said, well, let's don't use hepatic blood flow, you just lose 50 mils per minute, and we got rid of all that difference that you saw there. But this is only a small subset of drugs. So arterial clearance is a whole body parameter. The relevant blood flow limiting this value may be cardiac output, not blood flow to the eliminating organs, a completely different hypothesis. We published this, and a number of people and companies came to us and said, you know, we actually have data in the companies that show that clearance of the drugs is more than hepatic blood flow. We thought maybe there was extra hepatic metabolism. We went back and tested. No. None of that ever gets published because who's going to publish a paper that says I get data that's more than hepatic blood flow when everybody in the world thinks hepatic blood flow is the rate-limiting step for metabolism? But unfortunately, this only solves a small subset of drugs where IV-IVC is not successful, but pharmaceutical companies seldom move high clearance drugs through drug development. So the major IV-IVC problem is for low clearance drugs, where the measure of hepatic blood flow has minimal effect on clearance. So you can change it from 20 to 50 or to 70, and it doesn't help you in predicting the low clearance compounds, because it's really protein binding and clearance intrinsic that are important. So what about experimentals of protein binding? Are we making mistakes in our protein binding? It could be, because if we underpredict the fraction unbound, this would reason we get so many underpredictions. And people say, well, we do all these protein binding measurements, are they all wrong? I think they're not all wrong, but this could be a potential answer for the way we do these experimental methods. But another protein binding issue has recently attracted attention where addition of protein has been widely proposed to improve clearance predictions. In other words, take protein and add it to your mixture, and then look at that clearance intrinsic, and you'll get a better answer. So we went back and looked at this in a paper that was published last year in Drug Metabolism and Disposition. Does addition of protein to hepatocytes or microsome in vitro incubations provide a useful improvements in vitro and vivo extrapolation predictability? You can see from a bunch of my titles, I'm always asking a question, and the answer is always no. So does addition of protein increase? No. To date, studies examining this phenomena have not included the appropriate controls. We went back and looked at 60 drugs, 97 experiments. None of it predicts. And yet, there is data out there that says it does predict, but we didn't see it in terms of looking at all the data. We can't be sure, but I don't think protein binding are the major reasons for poor IV-IVC predictability. So when I did Kirchhoff's laws, I left out another entering process, and that's the transporters. So is the answer a function of transporters? So I can't go into this, but it is in our recent papers discussed in great details. But none of these advances in our understanding can explain why organ model independent, where transporters are not relevant, or organ model dependent when transporters are relevant, can explain why IV-IVC works for some compounds, but not for the majority of low extraction ratio drugs. So let me ask a question. What do we do in terms of these pharmacokinetics in vitro and vivo that really potentially could be different between in vitro and in vivo with looking at intrinsic clearance, and that's the volume of distribution. In our in vitro mixture, the enzymes and the drug are in the same volume, and we predict clearance related to that. But in vivo, the volume of distribution for the drug can be very different than the volume of distribution for the enzymes. And is that the reason we do such a poor job? And basically, we think it is the reason that we do such a poor job. What we're trying to do is take this in vitro one-compartment model where the enzymes and transporters and the drug all have the same volume of distribution and relate it to an in vivo situation. So can this be overcome? Well, last month we published our second Kirchhoff's laws paper, and what we did in that paper was to show that in fact you didn't need to use differential equations either in chemistry or pharmacokinetics to predict all these reactions. You can just use Kirchhoff's laws. But in chemistry, you're only interested in rate constants. In pharmacology and pharmacokinetics, you're interested in clearance. That clearance term has a volume term in it. So what we said is, can we take the Kirchhoff's law approach to everything we're doing and only determine the rate constant and look if that can be scaled up to the rate constant in vivo? And anytime there is more than one volume in pharmacokinetics or pharmacology, you're going to get the wrong answer the way we do it now because we can only put one volume term in that equation. So this could be analogous to what we've done IVIVC, one volume term versus two volume terms. So what's the hypothesis? In other words, go back and look at this multitude of data out there, and instead of scaling up clearance, scale up rate constant, because that's independent of volume of distribution. And see if it works. So we analyzed a limited database and didn't see it, but academics don't have that. It's only the companies that have that. They have these huge databases. They need to go back and look at it. So one of the first companies I presented this to did go back, and they did see the correlation in vitro, in vivo for the rate constant, although they didn't see it for clearance. So what do? If you can get it right, then you got to be able to predict volume of distribution. Now, actually, we do have some really good in silico ways to predict volume of distribution. So take your molecule, use its physicochemical characteristics, predict volume of distribution, multiply that by the rate constant, and see how well you do in predicting clearance. Now, I don't have the answer, but what we've been doing is not right. And I think this is a new way, and there's lots of data out there that can be looked at. It just hasn't been looked at. So this is only an untested hypothesis at the present time. We still don't have an IVIVC methodology that's successful, although the leading scientists in our field have been looking at this for more than 50 years and can't solve it. So my conclusion, published in vivo, venous measured clearances determined by single-dose AUC or steady-state infusions closely approximate arterial clearance. We're trying to solve arterial clearance. I strongly believe that the IV-IV interactions is due to theoretical reasons, not experimental reasons. We can get this simple relationship with Kirchhoff's laws. This is consistent with the finding that all the actual experimental data says the well-stirred model fits the data. None of these new findings explain why IV-IV is successful some of the time, but most of the time not successful. Could this be explained by the mechanism that I said, it's a volume of distribution? If so, could IV-IVC be used to predict in vivo rate constants, which can then be multiplied by a predicted VSS to predict in vivo clearance? So it's only a hypothesis. So I've had a lot of different collaborators, and since I'm saying everything we've done for the last 50 years is wrong, of course I can't get any funding, so I have to fund it all myself, but I'm able to do that. And if you'd like a copy of these slides, I'd be happy to share them with you. Thank you.